Hello and welcome to lecture 3 for the course on aerodynamic design of axial flow compressors and fans. In last lecture we have discussed about different types of aero engines, in which we have taken brief description about different engines. That's what has given you idea about what all are the application of gas turbine engines for aero application. We have discussed about the single spool configuration. We have discussed about the multi-spool configuration. Understand the thing, like they are having the special requirement. We are having different constraints with the single spool configuration, and that's the reason why we are moving with say multi-spool configuration. You may be aware of say performance map of my compressor, where we have discussed about say when the compressor that's what is rotating at the low speed, then there are chances for my front stages to get stalled or it will go under surge. Same way when it is operating at the high speed, my rear stages that will be going under the surge condition. So in order to meet the requirement for say wider operating range, people they are moving with the multi-spool configuration. Now we have seen this configuration of the single spool turbojet engine, double spool turbojet engine, high bypass ratio turbofan engine. We have seen low bypass ratio turbofan engine. Now let's move towards say high bypass ratio turbofan engine. So recent trend for the use of these aero engines, the high bypass ratio engine is a major contributor, because we can say we are having wide range of application for say your commercial aircrafts. Okay, with the increase of number of passengers, the requirement for the aircraft it's increased. With increase of number of aircraft, we are looking for more engines, but there is a global competitive market amongst these airline companies. That's the reason why they are looking for most efficient engines, and this is what is one of the priority for the future requirement of commercial aircrafts. Now here if you look at, these are the big size fan which are being used for turbofan engine. These fans are from Rolls-Royce engines. If you look at here, this fan, what we are talking of, that fan it is connected with all blades, they are connected with the fans. This fans, that's what is having the special application. Like this is what is a taller size blade, and we can understand this blade that's what has been fixed on the hub, and this is what is acting like a cantilever beam. Now if you look at, when I am having my inflow condition, say we are having say different kind of inflow condition, it may be say smooth flow, it may be say your distorted flow. Distorted flow, I mean there is a variation in pressure, temperature, total pressure, there is a formation of wake that's what will be striking, atmospheric turbulence that will be going inside the engine. All these things, that's what is creating the disturbance of the flow that's what is going inside. And since this is what is a taller blade, we discussed these blades, they are made up of aerofoil shape. So when I say aerofoil shape, it will be having its own differential pressure on pressure side as well as on the suction side. And because of this differential pressure, there may be chances there that there will be failure of this blade, or maybe it will be having the flutter of the blade. And in order to avoid this kind of problem for say high aspect ratio blade, or say for say turbofan engine fan blade, they are using these fans. Now when I am incorporating these fans, that's what is having some aerodynamic penalty. Okay, so earlier engines, when we are discussing say during 90s, people they used to use design of this kind, because high bypass ratio engine, as we have discussed, that's what is having higher thermal propulsive efficiency. Now on this side if you look at, these are the recent turbofan engine blades, fan blades, that's what is having a special kind of shape. Just look at carefully, this is what is having highly three-dimensional blade. Okay, So near the hub region, it's having some kind of design configuration. On the top side towards the shroud, if you look at, this is what is having a different kind of configuration. Let me show you here. So this is what is one of the blade. That's what is been provided by this Rolls-Royce. Okay, and here if you look at, say, up to some 50% of my span of this blade, this leading edge, that's what is having, say, circular shape or elliptical shape, and they are thicker. Now if you look at on the top side, this blade, that's what is having, say, thinner kind of configuration. So this particular section we are defining as a leading edge. So the leading edge of my turbofan blade, that's what is having, say, elliptical or circular shape up to initial stage, and then I will be having sharp leading edge. This sharp leading edge, that's what is because it has to handle the transonic flow, in the sense the formation of my shock. So this blade, that's what will be handling this shock, so that shock will be standing at the leading edge, and that's what is a special kind of design. And this is what is a most recent development. That's what these aero engines they are doing at this moment. Okay, here if you look at, earlier they were having number of blades. This blade may be in the size of, say, 1 meter, 0.8 meter. It depends on what is the bypass ratio. Okay, and you can understand, if I'll be taking one of the blade, that's what is having its own weight. Suppose I am making that blade from metal. Okay, and such number of blades, that's what will be increasing the overall weight of my fan. Now in order to avoid this kind of situation, people they move with the composite configuration. So Rolls-Royce is a company who has initially started with the development of these fans using composite structure. Now this is what is a parallel configuration. You can say for GE engine, they were also having the fans, that's what is in order to provide the equal spacing between the blades, and that's what is handling the problem what we are discussing in sense of structure. Later on they have developed the three-dimensional blading. Okay, here if you look at, this is what is one of the GE engine blade. Here also we are having, say, GE Gen X turbofan. These are the developments. You can see this is what is with CF60, this is what is with GE90, and this is what is most recent engine, that's what is Gen X. Okay, so all these blades, as I discussed, that's what is having its own weight, and in order to address that, people they are using carbon composites along with the leading edge, that's what is made up of your metal. Okay, so this course is mainly been focusing on the aerodynamic aspects. We will not be discussing details about the structure, and we will not be covering anything in sense of aeroelasticity. These problems are the major problem when we are talking about, say, our axial flow fan and compressor, but because of our constraint with the time and content, we will be focusing more on aerodynamic design. Okay, those who are interested can move forward with the understanding of this structural part. That's what is called aeroelasticity of these blades. That is also one of the challenging area. So based on your understanding of your aerodynamics, you can move forward with the structural part, or those who are having the background of structural, they can move with the aerodynamic design, and that combination is rare. And these days industries they are looking for such combination. So this is what is giving you hint in sense of in what direction you need to plan your activity. Okay, now let's start with the fundamentals of your diffuser. Okay, what we know, we have our one-dimensional compressible flow, and for that we have derived the equation based on my continuity equation. It says my change of area, it's a function of Mach number, and this is what is a function of change of velocity. Now let me consider, suppose say I am having subsonic flow. If that subsonic flow, that's what is entering inside my duct, my expectation it is to rise the pressure at the exit. So you can say at the exit I am looking for the rise of pressure. Suppose I am having my flow to be subsonic, so this term if you consider, this is what is my positive term. And here if you look at this dV by V, you can say I am looking for increase of pressure. That means I need to decrease my velocity. So what it says, I am looking for, say, the rise of pressure, and that's what is indicating my dA by A should be increasing. So that's what if I am putting, it says this is what is giving you the shape where my inlet diameter or my inlet passage area, that's what is smaller, and my exit diameter, that's what is larger. Now this shape, that's what is aerodynamically people used to say as a diverging passage. Okay, this shape, it is known as a diffuser. So basically what we say, we are looking for increase of pressure in our compressor. We can say we are diffusing our flow. Okay, so do not get confused with the terminology of rise of pressure or diffusion of my flow. Okay, so basically with this fundamental we are having some idea. If I will be having my flow to be subsonic, in order to increase my pressure, I am looking for the passage area. That passage area is of diffuser shape. Now you say, sir, let's move with the next requirement. That's what is say when I will be having my flow area, that's what is say supersonic flow. So similar in line to what we have discussed, my area ratio, that's what I am putting it as a m square minus 1 dV by V. Now for this supersonic flow, I am looking for the diffusion to happen. Now from this equation, if you look at, since my flow is supersonic flow, this term, that's what will be coming negative term. And our requirement, it is for compressing the flow. That means my dV by V also will be coming negative. Okay. So here in this case, this is what it says, my passage area for supersonic flow, that's what will be giving me the decreasing area kind of configuration. Okay. So here in this case, you say when my flow is a supersonic flow, and if I am looking for the diffusion of my flow, I need to have my passage as a converging passage. Now this converging passage we have studied in our gas dynamics. What it says, that's what will be subjected to thermal choking. So no, I will be having my diffusion of flow or say deceleration of flow from supersonic flow to m equal to 1 condition. So this is what is a region, I say this is what is my thermal choking region. So further deceleration of flow, that's what is not possible for my supersonic flow. Now in order to have that kind of configuration, I need to follow with say further diverging passage. Okay, so you can say now further deceleration of my flow from Mach m equal to 1 towards the subsonic flow, that's what is happening with my diffusing passage. Okay, so here at the exit, I will be having my increase of pressure, I will be having my decrease of velocity or my decrease of say Mach number. This is what we are defining as supersonic diffuser. So with fundamentals, what all we have learned in our gas dynamics, we will try to understand. We are looking for some devices, that's what is been used for raising of the pressure. And this raising of the pressure for subsonic flow, we are looking for the diffusing passage, that's what is having divergent shape. We are looking for supersonic flow in which my passage area, that will be decreasing initially and that will be followed by say increasing area, that's what we say converging diverging kind of diffuser. Okay. Now let's try to understand what is the application of what all we are learning here or what all we are discussing here. So this is what you can understand. We are having one diffusing passage. So you can say this is what is one of the diffuser, that may be of rectangular shape, it may be of circular shape. That's the reason why dimensional geometry, that's what I say W1 and R1. That will be having certain amount of length. So this is what is representing the length of my diffuser. This is what is my exit dimension, we can say that may be R2 or W2. Now this diffusing passage or diverging shape, we are having certain angle with the wall, that's what is defined as a diffuser angle. So you can say this is what is my diffuser angle. Now based on our fundamentals of say fluid mechanics, here if you look at, Suppose if I consider my flow, that's what is entering inside my diffuser, that's what is a fully developed flow. So this is what is representing the profile of fully developed flow. Now what is happening, if I am moving further downside, the shape of my profile, velocity profile, that's what is changing. Now near these two walls, if you look at these two walls, I'll be having this profile, that's what is changing, and it is deforming. It says my velocity is going to be say 0 near the end wall region, and in the center I will be having the flow to be having say uniform velocity. Now if I'll be putting my velocity triangle further down, I will be having different kind of configuration. So this is what is one of the application. You say now like we will be looking for some kind of configuration. Say people, they will be going very choosy. They will say unnecessarily, why do we increase the length of this duct? So they will say, let me reduce the length of my duct. Say this is what is say shorter duct. And if you look at for this shorter duct, you will be having my divergence angle, that's what is coming to be higher. Okay. So like without understanding of your aerodynamics, if you will started thinking of, yes, this is what is one of the possibility. We will be discussing what is that. Next configuration, it says I am having sufficient amount of length, that's what is available. So let me go with say longer size of duct. So this is what is say my longer size of duct. Okay. So this is what is my longer size. And if you look at, I am having my angle, that's what is say lower. Now for all these three configurations, if you look at carefully, that is what is having specific meaning, that's what is having specific application. Okay. So let's try to understand what is happening within this flow passage. So this is what we say in sense of my application, let's say. So here if you look at, this is what is representing my streamlines. These streamlines, they are following the curvature of my diffusing duct. You can say my flow is more uniform and steady in sense. So we can say this is what is say unstalled kind of configuration. So for most of the application, for many application, as aerodynamists, we are looking for this kind of configuration in which we are having this unstalled condition. Okay. Now like as we discussed, we will be having the change of dimension for my diffusing passage. And what it will be doing, if you look at carefully, from one of the wall, I will be having the formation of eddy or flow separation, that's what is happening. That's what is giving thicker boundary layer, okay, and that's what is giving erratic flow in that particular region. There may be little or say reversal of the flow, that's what is happening in that region. That's what I am putting that as a appreciable stall. Okay. Now like if I'll be going very choosy and if I'll be changing my dimension. So here if you look at, maybe I will be putting larger divergence angle. What will happen? My flow will be having separation to be taking place from both the walls. Okay. So this is what is very erratic flow. You will be having oscillation of pressure and my overall flow pattern, that's what is getting disturbed. So in overall, if you look at, it says when you are having your N by W1. So here if you look at, this is what is say my length of the duct and this is what is my entry dimension. It says if this is what is less than 4, so I will be having my flow separation that will be happening from one of the wall. Okay. If I will be changing that say in the range of 4 to 12, it says I will be having my separation of the flow that will be happening from both the walls. Okay. Now if I will be going very choosy and if I'll be putting that to be say more than 16, then you will be having other kind of flow structure. Let's look at what is that flow structure. So here if you look at what is happening, I will be having my flow, that's what will be getting separated from the one of the wall and that's what is giving the flow reversal. So you can say this is what is a region, that's what is making eddy. Okay, you can say there is a low momentum fluid, that's what is present in that particular region. So if I consider low momentum fluid, I can say in that particular region my velocity will be nearly 0. So this particular region, that will be acting like a solid wall. So what will happen? My flow will be getting deflected towards the other wall. And if this is what is your case, we will not be getting what pressure ratio we are expecting or what pressure rise we are expecting at the exit. So that's what is called fully developed stall. Okay, there may be chances you will be going very greedy, and for going to greediness, it may happen you will be having two such kind of bubbles. That's what will be forming near your end wall region. Okay, near your diffuser wall region. Now what will happen? This is what is acting like a wall for both the wall side, and that's what will be giving you nearly jet kind of configuration or constant area configuration. What we are looking for here? We are looking for rising of pressure, means we want to diffuse our flow. In rather going for diffusion, what is happening? Here we are accelerating our flow. Okay, so this is what is very important when we are discussing our understanding for, say, diffusion process. Okay, let me move towards the next. This is what it says. My stall diffuser, that's what is a function of my inlet geometry. It's a function of my outlet geometry. It also depends on my Reynolds number, what is my inflow condition, what is my outflow condition, and like the geometry of my diffuser. Okay, so here this is what is a very good compilation of data. That's what was given by Klein and Fox. They have done the experiments for, say, different shapes of diffusers, and they have come up with this kind of plot. That's what is universally people they are using for the design of different diffusers for various applications. Okay, so here if you look at, as we have discussed, let me go selectively. Let's say we are selecting my N by W1 as, say, 4, and if I am extending that on my y-axis, that's what is giving me my divergence angle. What it says, if I will be having my divergence angle, that's what is, say, less than 14 degree, I will not be having any stall. That's what is happening, and that's what is my requirement. That's what is my requirement. Okay, now here if you look at, if I'll be going slightly greedy and if I'll be putting my angle slightly larger, say I'm taking that angle, say 18, without understanding. So what will happen if we are going with this? We will be having your appreciable stall that will be forming. Okay, so being engineer, we always need to have our understanding for the design for our diffuser. So when we are designing our passage, it should not be without understanding, and this is what is one of the best example. Let's say, suppose I will be going slightly on the higher side. I say I will be having my N by W1, that's what is, say, 10. Okay, I'll be making my diffuser, that's what is a short diffuser in that sense, okay, with larger diameter. So if that's what is your case, you will be having your 2 phi or your divergence angle, that's what is coming to be different. Okay, here it says you need to go with the angle of, say, 7 degree or 7.5 degree. If I'll be increasing my angle other than that, that's what is giving me all kind of flow configuration. Okay, so this is what is one of the fundamental, that's what is required for the design of my diffusing passage. Let's try to understand what is the application of that. Okay, so let me go to the next slide. Here if you look at, this is what is representing my area ratio and my divergence angle with respect to my pressure recovery. Let me tell you what we say in sense of my pressure recovery. That's what is nothing but the rise of my pressure. Means what I am expecting in sense of my diffusion of the flow. Now for that configuration, as we look at, it says when I am not having any appreciable stall, I will be getting higher total pressure recovery. That means we are getting what diffusion we are looking for. Okay. Now if I will be going with the increase of my area ratio, here if you look at, it says that will be going to, say, large transitory stall, and my pressure recovery, that's what is going to reduce. Okay, if I will be going so greedy, then there may be chances that I will be having two-dimensional stall, and further increasing it may give you jet flow. Okay, so this is what is very much required when we are discussing for, say, designing the diffusing passage. The question may arise in your mind, sir, why we are discussing about this diffuser? Okay, what is the use of this data? I will be correlating this with the design of my compressor passage. If you remember, we were discussing about the high bypass ratio engine where my duct, that's what is connected with, say, low pressure spool and high pressure spool, that's what is connected with the passage area, that's what is called diffusing passage. So there also I will be having the application for this. So there are different kind of shapes. We are having rectangular shape, maybe we will be having circular shape, we will be having, say, co-annular kind of shape. So this is what the fundamental, that's what will be helping to us. Okay, now say this is what we are planning to discuss, okay, in sense of our application for the understanding of the diffuser. So here if you look at, this is what we have discussed. So this is what I was talking to you in sense of my LP compressor stages, that will be followed by HP compressor stages, and here we are having interconnecting duct. Okay, now if you look at carefully this passage, that's what is having a specialized shape. Here also we are having the specialized shape. Okay, we will be discussing about this in fundamental. Okay, now if you look at carefully, this is what is representing one of the cut section. So if you look at, we are having two blades, that's what is being arranged in one rotor. Okay, now if I consider I am having my rotor and stator. Okay, so at particular station, say my mid station, if I will be cutting my blade, that will be having, say, aerofoil shape. So like, remember one thing, these blades of rotor and stator, that is made up of number of aerofoils. Okay, we will be discussing what all is the meaning of the aerofoil, but here just look at this blade, it is comprising of number of stations. At all stations we may be having different aerofoils. Okay, they are being stacked in a systematic way in order to meet the requirement. Okay, now if I look at the passage between these two blades, here if you look at my entry area, that's what is a smaller area, and my exit area, that's what is a larger area. Okay, so if you recall, we were discussing about the diffuser. That diffuser is having similar kind of structure. Okay, so we can say between the blade passage we are having the shape, that's what is a diffusing shape. So what all fundamentals what we have learned for the diffuser, that's what is straightway applicable here. Okay, now if I will be putting these blades, if I will be putting that together, and in between passage if I will be putting, you can say this is what is my hub section, my mid section, and this is what is my shroud section or tip section. So this is what is giving you highly three-dimensional shape within the passage. So you can understand the diffusion, that's what we are doing in my compressor, that's what is being done within this blade passage. Let me show you, say this is what is we are discussing about. So here in this case we are having, say, two blades. So these are the two blades which are being arranged. Okay, so here if you look at, we are having leading edge, we are having trailing edge. Okay, this is my leading edge, this is my trailing edge, and if you look at within this passage, I am having my flow, that's what is getting diffused, that's what is having diffusing shape. If you look at, we are having larger area and smaller area. Let me put this in a way. So as I told, my compressor blade, that's what is made up of number of, say, aerofoils. So if you look at, this is what is one of the station. So here on this side what we are looking at, that's what is, say, my suction surface, this is what is, say, my pressure surface, and if I'll be putting this, it says this is what is having diffusing shape. So this is what is near your, say, tip section, this is what is near to my, say, mid section, this is what is near to my, say, towards the hub section. So all this, if you look at carefully, this is what is making a diffusing passage. Okay, so like what all fundamentals what we have studied for our diffuser design and diffuser aerodynamics, that straightway will be application to this axial flow compressor and axial flow fan. Okay, so here we are stopping with these fundamentals. In next lecture we will be discussing further. Thank you very much for your attention. Thank you.